Okay, so let's continue with our tutorials on statistics for engineers, SENG 302. So in today's session, we'll be doing the first part of random variables, and then we are going to consider major things, right? So first, we'll talk about the expected value, um, and then we'll move on to talk about binomial distributions and Poisson distribution. I think basically that will be it for random variables 1. So let's get to the main thing. What's a random variable? Random variable is simply a function, right? So it's not a number. It's a function that's used to estimate the outcome. Sorry for my handwriting. Outcome of an event. Okay. So it's basically like a set of probabilities. You're trying to calculate probability of. So you have the probabilities, okay, or maybe you can calculate the probabilities of an event. But then random variables allow you to estimate the outcome of, say, some um, probability in that whole set. So, for instance, you have a die, right, or maybe two dice. So, what would be the probability that tossing a die maybe 500 times, you get a particular outcome? So, that's where you have random variables coming in handy. We have two major kinds of random variables. We have the discrete. So, discrete are things like, say, so discrete variables basically. Then you have things that are distinct, so number of sides of a die, maybe number of people in a class. So you can't have, say, you have 35 and half people in your class. You don't have anyone being a half person. So yes, so that's discrete variable. We have continuous. So with the continuous, how do you spell that word? So with the continuous, we have things that can vary over the scale. Okay, so like length, mass, all of those things are continuous variables. Now, when we come more into understanding what random variables are, then we'll talk more about, say, distributions, right? So let's say you have, so let's just take the die example for now. So you have a dice, right? Now, with the dice, you have 6 sides. The probability of each side, provided is a uniform die, then you have same probabilities for all sides. So if we pick any die, let's just do this real quick. So let's represent this with x, 2, 3, 4, 5, 6. Okay, and then probability of x. Now we know the probability of each of them happening is basically the same thing. So yes, so the probability of all of this is the same. Now, what are we going to do with this? There are a number of analysis we can do with this. So, for instance, we can do cumulative analysis. So, we'll find the cumulative distribution of this. So, if you find the cumulative distribution of this, then it will basically be the probability at each x, right, in addition to everything behind it. So, that's less than or equal to. Okay, yeah. So probability of x less than or equal to that number. So here less than or equal to 2, right? Less than or equal to 3. So in that case, you end up having things like 1 on 6, 2 on 6, 3 on 6, 4 on 6, 5 on 6, and then 6 on 6. So if you draw some kind of a graph, it will look something like this, right? Some staircase, so it gets to 6. So basically, that's cumulative variables, right? Now, yes, so we have something we call expected value. Expected value, one way to look at expected value is looking at like a mean, okay? So you can look at expected values like a mean. Now, is denoted as E of x and is calculated as x times probability of x. So let's just say summation, okay? Yeah. So for this one, if you look at it clearly, then you can see that okay, then the expected value will be 1 times this plus this time this plus this time this plus this time this, in that order. So you just add everything up. So for something like this, if you actually calculate it, we can try it out. So you have 1 times this, that's 1 on 6, 1 on 2, 1 on 3, 1 on 2. Yeah, so everything when you add it up, I think it gives like 3.5. You can try this out. So it gives like 3.5. Now that means that the expected value after tossing, right, you should be getting 3.5. But then you know that this is not realistic with a dice because it's a discrete scale. But then it just gives you an idea of what you should be expecting at the end of an experiment. So if you take let's say any event at all, right? What are the possible expectations? So this one, the expectation is that you can get 3.5, but then no one really gets 3.5 tossing a dice. But then it's just the idea, okay? There is there's an example in the slide, so we can just try that out. So it says that um, so you have a group of people, I think a third class, and then the number of hours they use for some activity. Let's just call it X, and then we can range it from 1 to 3, right? And then you have the probabilities being this. Yeah, it's sometimes it's always really essential to understand the main idea behind what you're doing. Okay, so something like this, right? So let me just read it out. So it said that third class had been it was surveyed regarding the number of hours that they played electronic games each day. So this is the number of hours people used to play games each day. So some people play 0 hours to 3 hours. Now, and the probability of getting someone is this because they interviewed a number of people, so you could calculate the probabilities. Now with this one, if you pick someone to random, what is the expected number of hours they use to play games? Hmm, okay, so let's just write out. So you take summation of what x, so you just go straight away. In some case, you don't have to waste time. So this time, this time, this time, this. Then what do you get? So you get something like so that'll be 0.4 plus 0.4 plus 0.3. So that gives something like 1.1. So that means that if you pick someone as random, then they are expected to have spent or would spend 1.1 hours of their day playing electronic games. So this is just the whole idea behind expected value, and it's calculated as simple as that. So no matter the scenario they give you, it's still the same thing. Now, we can get to a point where we make it more explicit, right? So we can make it more explicit. Then we say that the mean, right, can equate the mean to the expected value. I'm so careful sometimes doing this, but yes, it's the same thing, right? So basically, you can equate the mean to this, and then this is the formula we started with. Now, once we know this, then they can ask you a number of questions. Once you have mean, you have expected values, then they can ask you a number of questions. They can ask you for variance, for standard deviation. So let's just put down some of the formulas we have for these things. So we know that standard deviation squared is variance, right? Yeah. And then, I think he will give us these formulas, so you don't really need to memorize them. But then it's good if you know them, right? Um, and it's the same thing, right? These things are the same. Or, in simple terms, if you just want the variance of x, then you can say is this minus mu squared, where mu is what the expectation. Okay. Yeah. So this for variance. Okay, so now let's pick some example. So let's consider an octahedral die. Octahedral die, right? An octahedral die. Okay. So if you consider an octahedral die, so this is an example in the slide. I think we can just solve it out. So, and then it says that what's the expected value of the number of outcomes when a fair octahedral die is tossed? So if it's octahedral, then we are expecting that it should have about how many sites? It should be having about okay. So if it's octahedral, then you should be expecting about 8 sites. So something like this, right? And we want to calculate the expectation of tossing this kind of dice. So how do you go about it? Now we know the formula. We've already stated these premises. So now let's just go ahead and calculate the expectation of this. Now expectation will be this times this. So we can just go ahead and do x p of x. Okay. So this time this you get 1 on 8, 2 on 8. Sometimes it's easier to go with the same what they call it, the same denominator, so that it does not complicate your life. All right. Okay. So you can add. Okay, so you should be getting something like 36 on 8, right? That's if you add it up. So 36 on 8, then you can decide to break it down, and that will be the expectation. Okay. And then what's the next question? It says that what is the variance of the number that comes up when a fair octet hit. So yes, so what is the variance, right? Now, how do we calculate variance? So let's refer to the formulas. Okay. So this was how we calculate variance. So variance is calculated as this minus mu squared. Now we know mu to be the expectation. So we have that as 36 on 8. So we just keep that. But then we need one more thing. We need this. So how do we get that? Let's come and fetch that from the table. So depending on the nature of the question, you might decide to do whatever you want. So we do s squared p of x. Okay. Then so 1 squared is still 1, then this still gives us 1 on 8. In that, 2 squared still is 4, so you get 4 on 8. Then we have 9 on 8. So let's just go straight and then do this. 25 on 8, 36 on 8, 49 on 8, and then 64 on 8. Now, when you do the summation, okay, so if you do this addition, I think you should be expecting something like 169 on 8, right? Yeah. So just in case you get something different, you can just put in the comments, right? So now with this, you can go ahead to do the analysis, okay? So you are expected to find the variance, and then I showed you the formula here, right? That the variance is this squared. So expectation of x squared minus mu squared. Then we just take that. So that will be this minus that. Okay. So expectation of x squared minus mu squared. Then that gives us 169 on 8 minus 36 on 8. What do we get? So we get 133 on 8. I guess that's correct. Okay. So this becomes our variance, right? Now if you want your standard deviation, you know what to do to it to get it, right? So basically, and then if you want your standard deviation, you just take the square root and then you get your answer. So basically, this is the idea behind expectations, right? So that's how you calculate the expectation of an event. So no matter what they give you, you can always calculate it out using the same procedure, same formula. It doesn't change. Okay. Now let's move to the next one. The next one is binomial distribution. Let me see if I have it here. Okay, so let's move to the next one, which is binomial distribution. So binomial distribution relates to what mostly I think what we did in high school in relation to binomial theorem, right? That thing where you have some Pascal triangle always going up and all of that. Yeah, but then in simple terms, you can express the binomial theorem with this equation, right? So you have n choose x probability. So p this will be the success. So it depends on how you do your notation. So this can be the success and this can be the failure. I'll explain that later. But then you have your p power x q power n minus x. So these two mostly sum up to 0. It looks like they are the complement of each other in this whole setting. Now, what is a success and what is a failure in terms of binomial distributions? So if we talk about a success, it's basically achieving what you set out to achieve. So for instance, you want to get 3. So let's say you roll a dice, right? You want to get 3. Then this 3 will be your success. Anything else to be a failure. So that's in the same sense, not necessarily the literal sense of success and failure. And then if you want to calculate your mu, which is your expectation or your mean, then you just multiply n by p. So the number of times you're doing that test, right, or the number of trials you are doing, multiplied by um, the success. And then if you want the variance, then you multiply the number of times by the success and by the failure. And then if you want your standard deviation, you take a square root of your variance and you have it. So one thing to note is that the success and failure are always complementary. They sum up to one. And then if you run independent trials, then you can apply this formulas to understand the probabilities that will come into play in a natural event. So let's just get some questions to understand what all of this really means. Okay. So let me reiterate some of the variables in the binomial distribution. All right. Okay. So we have a number of trials, right, or a number of ways in getting what we want. Um, then probably this is just what we want, right? Then this will be your success, this will be your failure. Let's just keep that in mind. Okay, so we have a simple question here. It says that say 40% of a class is female, right? And then um, the probability that 6 out of 10 students walking in will be female. So you have 40% of a class being girls, and then um, 10 people just walking. So what's the probability that 6 of them are females, right? Now, so let's just get it and see how we'll go about with it. So you have 40% of the class being female, and then 10 people walking. Okay, of course, 10 students walk into the class from the same class. What's the probability that you have 6 of them being female? Now, with such a question, you have to apply the binomial distribution because you can't solve it directly, right? So, first of all, what is our success and what's our failure? Our success will basically be someone being a female, so which is 40%, so 0.4, and our failure will be someone not being a female, right? And that'll be 0.6. And then we have 10 people, so 10 to 6, so the probability that the person will be a female will be 10 choose 6 or 10 combination 6 multiplying 0.4 exponent, then we have a 6 up here times 0.6 exponent, the difference, right? Then that will give us 4. So when you compute this, you should be getting 0.115. That's the same as 11%, which makes sense because in the first place you said that the girls were 40%. So if 10 people walk into the class, you don't expect the majority to be females, right? So that's why you have 11% for this. I hope that makes sense. So that's basically it about the binomial distribution. There are other forms a question could take. So probably after asking you this, then you can be asked, okay, so let's say we do the test maybe 100 times. Then what should be the expectation, right? What would be the variance? What would be the standard deviation? It's basically the same approach. Now let's look at a similar example here, where we talk about um, okay. So let's consider another example, right? Where you have say 100 flips of a coin, and then you want the number of times a head will come up. So let's say we are tossing the coin 1,000 times, right? We are flipping 1,000 times, and then we want a head. So what is the probability that you would actually get okay, so in the first place, the probability of getting a head or a tail is a coin, so 0.5, each of them takes the same thing. But in some instances where it differs, then you have to apply it. So because it differs, what would be the expectation? Well, the expectation will simply be your number of times the probability, or I call this probability, but it's actually the success, right? The probability of the success, which is 0.5. So that will be 1,000 times 0.5. So this will give us our expectation or our mean. So that means that this gives us 500. So in other terms, if you toss a coin 1,000 times, you should expect half of it to be heads. That's the expectation. Is the mean. Okay. Now if you want to calculate the variance of this, then you do this multiplication. You multiply the two events, that's the success and the failure, by the number of times. So this one you have 0.5 times 0.5. Okay, in order. Then you have 1,000 here, right? And then we'll be getting something like 250. And then if you want your standard deviation, then you take the square root of 250. Then you get your answer. So that should give you approximately like 16. Okay. Okay. So this is for your binomial distribution. So that's how to solve binomial distribution. So for instance, if they ask you if a coin is tossed 7 times, so what's the probability of getting 3 hairs? Right. Then you use the same formula. Now n will be 7. If you're looking for expectation, it's quite easier, right? And then the probability of getting 3 hairs, then that would be what? You know the probability of getting a hair in a coin or a tail is always 0.5. So your probability of success is 0.5 and your failure is 0.5. So with that in mind, then you can go ahead to use this formula, n choose r, times your success power r cube power n minus r. So you can go ahead to use this one. So it can look like 7 combination, 3 times 0.5 power 3 times 0.5 power what is it? Then that will be the difference, right? Then that will be power 4. Okay. So basically this one will give you the answer to that question. I hope that is fine. Okay. So basically this can apply to all other instances that have to do with binomial distribution. So you are basically trying to understand how the outcomes of events will vary, basically. Okay. So now let's move to the next one. We call it the hypergeometric distribution. Okay, hypergeometric distribution. Okay, so if we talk about hypergeometric distributions, right, we're simply talking about distributions where you do sampling without replacement. As simple as that. So if it's so let's consider some of the examples we used to do. Now you have, say, a box, right? Let's say you have a box full of balls, right? So you have red and blue balls, right? So red and blue balls. Now if you take one red ball out without replacement, then you know that whatever is left inside there is less one. But then, okay, so with that you can simply do your calculations, right? Because if you are taking without replacement, then it's easier to calculate because the probability changes with time. So let's say you have okay, so let's say we have one black ball, and then say, okay, let's use the red and blue again, right? So we have 3 red, 3 blue inside the container. Now you pick the first one. Now the probability of even picking a red in the first place will be what? That would be 3 or 6, right? And then let's say you picked a red ball, then you have 2 more red ball left. Then the probability of picking a red ball at that instance will not be what? That would be what do you call it? That would be 2 on 5, right? So with this kind of, you are not replacing, so you know what the instance would be. Now in an instance where immediately you pick it, you replace it, then it looks like nothing is really happening. So at every time it looks like you're starting the experiment from scratch. So each trial is independent. Okay. Okay. So let's just get to some of. Okay. So I have this thing here. these formulas here, and then that's what you use to calculate your hegemonic distribution. It's just the name. It's not any big thing. Okay. Okay. So with this one, you just have to know two major things, right? As you can see, it's just like you have some total number, then you take out r, then that is, so you have some number, right, r, then you are choosing x. So you have, let's say, five things and you are choosing two. It's the same thing, the combination. Then the remaining of that, then something else is choosing something. So let's say um okay, so let's say you have like a box made up of, say, um 10 white and black balls, right? Then your probability of choosing maybe one red, sorry, one black that um, from that combination for the first time. Then you can guess maybe from your 10 you are choosing one, right? But then that's not the end, because there are other things in the box. So if you are choosing that too, then let's say you want to choose a white too, then in that case have 10 choosing one. So it's just like you have two instances that kind of coincide with each other. So you have two classes, class 1 and class 2. Okay. So basically, so that's just it. I think it would be better to explain it more with an example. Let me see if I get an example for us to discuss. So basically, your n is your total number of elements, right? The total number of elements you have, and then I think I didn't write my this one. So this one is a capital N. That's the total number of elements, and then this is small n, which is the number of elements drawn. Okay. Now x will be the number of successes in this element. So the number of successes in the main n elements, and then x is the number of success in the, so it's, yeah, so basically that's just it. So you have your r, sorry, so your r is the number of successes here, and then x is the number of successes here. Okay. Okay, so I think there's an example here. We can try this out. Okay, so it says that a lake contains 600 fish, right? So given that, so let's put our premise. So we are given that a lake has 600 fish, and then 80 of which are tagged. So 80 are tagged, right? Okay. And then a researcher randomly catches 15 fish from the lake. So the researcher catches 15. So find a formula for the probability mass function of x, the number of fish in the researcher sample which are tagged. Okay. So now this question, let's just take it one after the other to see what we are really looking for. So first of all, we are looking for, so first of all, what's our r, right? So our r will signify the 80. I guess that makes sense, because 80 is um, the number of fish of interest, right? And those are found inside 600. So this one will be a big N, and then this will be a small r, right? So that's the first choosing. So the first class of selection we did was choosing 80 fish out of 600 and tagging the 80. That was the first one. Now the next thing that we are trying to consider here is, well, we have some other, um, so we choose 15, right? So later on went and chose 15. That's our class 2. So those 15 fish, right? So we are looking for some x out of that 15 that are tagged. I hope that makes sense. So if I write down our formula, then how would that be? Then the probability of x will be our r choose x. So what's our R? Our R is 80. Choose X. Well, we don't know our X yet, so we are just choosing something. And then this one will be 600 minus what? 80, which gives us 520. 520 choose what? So we'll be choosing our small n minus x, which will be, we don't have x, so we just go with this. Okay, then all over the total, that's 600, choose 15. I hope this whole thing makes sense, right? So let me just reiterate it. All right, so you have a total number, right? So you have two classes, and then one class is kind of the bigger set, so your class one is kind of the bigger set here. So you have 600 fish, right? That's in your class one, and then out of the 600, 80 of them are tagged. So if 80 of them are tagged, then that forms your class one. Now the next time someone picks 15 fish out of the 600, you just want to estimate, right, how many of them are tagged. It's just that simple. So we'll go through the same formula again. So this is called hegemonic, hypermonic, sorry, hypergeometric something. Yeah, so hypergeometric distribution. So first of all, we take our R combination, our X, and then we take our remainder, right? So the remainders combination each other. Then we take the totals combination each other too. Yeah. Okay. So this is the expression for. So this is what the question was asking for. It was asking for the expression or the formula that shows the probability mass function of X. Okay. So basically this is it. And then if you were given values, you could go ahead to solve it to find the probability. Okay. So for instance, if they ask you what's the probability of finding maybe 10 of them that are tagged, then you should be expecting to get a very, very low number, which makes sense. Okay. Okay. So there is another example here. Okay, so with this idea, I think the example should be fine. But then let's move on to this this third example, and then we'll move on to the next thing. There's an example. Okay. Okay. So there is an example that says that a random sample of 5 students is drawn without replacement from 300 seniors, right? And each of the 5 seniors is asked if he or she has tried a certain drug. So suppose 50% of the seniors actually tried the drug. So we are doing without replacement, here. Now, what is the probability that two of the students interviewed have tried drugs? Okay. So first of all, our bottom line. Okay. So now let's just get our bottom line straight. Now we are looking at probability that x is equal to 2. So we have our x already. Okay. Okay. So we have like two major classes here, right? So we have a class of 300. So we have our class 1 and our class 2, as we said at the beginning. So now the probability at x equals 2 would give us, so first of all, our R. Let's suppose 50% of the seniors have actually tried the drug before. So if 50% of this have tried the drug before, then that gives us 150. Then how many people do we want out of the 150? We want to find 2, just 2, right? Then the rest gives us what? So that would be 300 minus this gives us 150. And this one, we said we picked 5 students, so 5 minus this, then that still gives us 3. Then all divided by the total number combination, your interest. So this thing is quite pretty straightforward. So your hypergeometric probability would be something like 0.3146. So basically 31.46% chance that two of them actually took the drug. This makes sense because you have say 5 people, you are choosing 2 out of them. Meanwhile, you know that 50% of people have actually taken it. So yes, so that should be sensible enough for such kind of a distribution. Now let's move to the last form of distribution we'll be talking about today. We're talking about the Poisson distribution. How did I misplace this? So we'll move on to Poisson distributions. But before we do that, I'd like to make a small comment on the hypergeometric distribution before we move on. So the bottom line was that we are doing this without replacement. Okay. So if you are doing it without replacement, then depend on the number of times you are doing it. So if the number is small, I think I made a comment about this one. So where we said that okay, so for the first time, if it's red and I think blue, then for the first time, if they are the same, then you should be getting 0.5. Then as it keeps on decreasing. But then if you have like large numbers, that's where it's very necessary to use your hypergeometric distribution, because if they are small numbers you can easily do that, but then if they are really high numbers, you are talking about say 300 fish or maybe 150 students, you don't want to sit down to do all of that one after the other. So that's why it's most essential to use your hypergeometric distributions. Okay, now let's move on to the next thing, that's the Poisson distribution. Now understand that everything we are doing now is still under discrete what? It's still under discrete probability distributions or discrete variables. Or, yes. So you can just classify everything as under discrete variables. Okay. And then if you're working with Poisson distributions, then we are considering events that have fixed intervals. So you have fixed interval from one thing to another. So in the literal sense, right? In the literal sense, jumping from one parameter to the other, you would be simply doing it by like exact um, exact intervals. So if an event is such that has this kind of exact intervals, then you can make use of the Poisson distributions. Okay. Okay. I think I have something here. Let me read it out for you. So one thing to also note about the Poisson distribution is that it evaluates the probability of a usually small number of occurrences out of many opportunities in a given period of time, area, volume, weight, or anything, right? So you are trying to evaluate the probability of something that is very small, a small occurrence in a very large set. So say um, getting what is very rare. Okay, so let's say today, as it stands, getting someone who has COVID, okay, who still has COVID, among say 1 million people. It's just the idea, right? Now, Poisson distributions are applied in fields like telecommunication, astronomy, biology, management, finance, and finance to estimate losses and claims in a given period, seismology, radiography, and all of that. So, Poisson distributions actually have real world applications, because for most applications you can assume that the intervals are kind of fixed. So if you have fixed intervals, then you can use the Poisson distributions. Okay, so let's get to the main formula and break down what everything in the formula is made up of. Okay. Okay, so in your formula you have lambda power x e power negative lambda all on x factorial, right? Now this your lambda is simply the average number of events in the interval. So let's say um, what's a good example? So okay, so let's say something like in a year you have a particular set of programs. So let's say in a year you have every year you have 3 programs, right? Every year you have 3 programs. Then your lambda will be 3. I guess that makes sense. So the number of events in the interval. Okay. E is the Euler number, which we know has a value of 2.71828. Okay. So that's basically the Euler number. So I think that's all. That's all you have there. So you're trying to estimate the probabilities of things that have small chances. Okay. So let's take an example. So say in a given stream, there are average of 3 stripped trouts per 100 yards, right? So we are talking with a fixed distribution here. So every time you get 3 trouts per 100 yards, right? So, or maybe, so let's say we have the whole lake here. Then if this is 100 yards, then you get three. So in that sense, right? And then, so this 3 will be our what? That will be our lambda, because that's the number of occurrences in the interval. And then your next thing will be your, so we have E already, that's your Euler number. It's always given to you. So let's go back to the question. It says that what is the probability of seeing 5 trouts in the next 100 years? Okay, so what is the probability of getting 5? Then you're just looking at the probability at x equals 5. So if you look at the formula, it's quite straightforward, right? Because we have lambda, which is now 3 times lambda power x, sorry, that's power 5, times your Euler's number, spend a negative lambda, all on 5 factorial. So what is this doing? What this is doing is that it's trying to estimate the possibility of this event, given that some things are constant. So here, we already know that in every 100 years, you are not going to get 5, you are going to get 3. So if you calculate this, you get something like 0.1008, which is basically 10% chance. Or so you have a 10% chance, at least. There is still a chance. So okay, yeah. So there's still a chance that you can get in one field, you can get up to 5. But then in Poisson distributions, we consider strictly standard deviation, standard intervals, right? Or a constant interval. So that makes sense why this number is getting low. I think if we try to experiment a little by using a number like 3 in our calculation to see what we will get. So maybe we can try that out and see if the number makes sense. So let's say you use 3, then what answer would you be getting? Should you expect something like 100%? I think that'll be fun to try out, right? Okay, so let's get to the next thing on Poisson distribution. So it says, so the next question says that on a particular river, overflow floods occur once every 100 years. So overflow floods occur once every 100 years. So what's your Euler number? Once every 100 years, so 1. You're considering 100 years. Now calculate the probability of K. So 1 to 5 overflows in 100 years. So you can always do this. So let's see, you want to calculate 1 overflow, right? Then that'll be 1 over, say, 1 power 1 times e power negative 1 all on 1 factorial. Basically something like that. So you should be expecting, you get the idea, right? So for 1 overflow, then this is the probability you should be expecting. But then as you increase the number of overflows, so this one, it was just the idea. You won't get 100% actually. But then if you increase the number of overflows, then you should be expecting less and less of a probability, because in the first place, it said that 1 overflow happens every 100 years. So according to this distribution, then you should not be expecting to have say 2 or 3 or 4 overflows in a year. So that just offsets the balance. Okay. So let's continue a bit with the Poisson distribution, and then okay, I think basically that's all for the Poisson distributions. So let's just do a short recap of what we've been doing in this session. So in this session, we're trying to analyze random variables. Okay, we are trying to understand random variables 1. And in random variables 1, we started off by talking about um, e of x, right? That's the expected value. So let me just say expected value. So we started off by talking about expected value, and with expected value you can, so it's just like the mean, and with that you can use to calculate the probabilities, like your variance. So you can use to calculate your variance or your standard deviation given a particular set. Alright, so given some analysis you can do that. And then the next thing we went on to talk about, so we spoke about binomial distributions too, right? So binomial distributions, you are trying to, okay, so you are trying to analyze the possibility of something happening. You're just calculating the probability of success or failure, right? So you know some success criteria, failure criteria, and then you're just trying to estimate the probability over a number of expectations, a number of instances. And then we moved on to talk about our hypergeometric hypergeometric variations, or you can just say distribution. In the hypergeometric distribution, we are trying to analyze some system, right, without um, replacement. So we are just doing some sampling without replacement. So we are taking our samples and then we are not replacing them. We're trying to understand how, maybe over a particular number, how it will behave. And then in that hypergeometric calculations, you have your first class, your class 1, and then your class 2. And then most of the time your class 1 is like the major subset of your class 2. And then we moved on to talk about the last thing, which we just spoke about, which is the Poisson distribution. Poisson distribution. And in the Poisson distribution, we are trying to um, calculate the probability of an event happening, given that we know that something happens at an equal interval in every period, right? So we have some period, and then what happens like equally in each of the intervals. And then in Poisson distribution, one thing you should notice that it depends on how they ask the question. So let's say they tell you that one flood happens every 100 years, right? Now calculate the probability of a flood happening in 50 years. You should not expect your Poisson distribution, your lambda to be 1 again. So maybe one way you can just do it is, if 1 is equal to 100, right? Then by looking at lambda at 50, then you can just do this and find your lambda to be 0.5, right? Or 2, sorry, 2. Then you find your lambda to be what am I saying? Yeah, so basically, yeah. So that's just it, right? Then you find your lambda to be 0.5, and then you move on. Yeah. So basically, that's just it for your Poisson distribution. And then this makes up for, so all of these are, so everything we've done in this session, they are discrete, right? So they all fall under the discrete variables. So moving on, we'll do the random variables too, and then that would be more of continuous data. Okay, so thank you, and then I hope you learned something from this session.